Let's welcome her.
Thank you. I would like to thank the organizer for giving me the opportunity to speak here. This is a joint work with Ralf, Schmidt, and Shaoyun, which I'm going to talk about. So it's about an equidistribution theorem on automorphic representation of a group called GSP4. So I'm going to define what does automorphic representation mean and what is this group. I know a lot of people will be not familiar with it. But I really want to start this talk by talking about some classical result of equidistribution. So one of the classical result of equidistribution is about taking curves like elliptic curve, which has an equation of this form, and it's the elliptic curve over Q. So think about, if you're not familiar with elliptic curve, think about this is a curve, cubic curve in X and Y variable. And here is one of the real locus of one such curve. Now, what you can do is associated to this curve, there is some arithmetic object which is called, denoted as E of AP of E. And this actually counts the number of, is related to the counting the number of points on this curve over the field AP. So if you think about the finite field AP, and then you can take all this coefficient and you can take mod P and you can look at how many solutions are there of this elliptic curve. And then there is this arithmetic object which is defined this way. And there is an equidistribution theorem which says that if this curve does not have a CM, CM is a special kind of curve which does not satisfy this kind of equidistribution, but we assume some kind of a condition on this elliptic curve, then it says that this normalized value of these APs, they are equidistributed in the interval -2 to 2. So there is, whenever you're talking about the equidistribution, there is a measure associated to that. So actual form of this Sato-Tate conjecture, which is this Sato and Tate, they actually built this conjecture in 1960. And this conjecture is generally formed in this limit form, that you take any sub-interval inside the interval -2 to 2. Let's call it alpha beta. Then you count how many of these numbers AP over square root of P's are there, and you take this ratio basically. And then it says that that number should be equals to this integral. So here the measure is 1 over pi times this function. So it's equidistributed with respect to this. So if you think about, I don't have like a particular curve here for this particular example I started with, but it's generally satisfy a curve which looks like this, where this is -2 and this is 2, and the values of these numbers right here, they should be equidistributed inside this curve. So this Sato-Tate conjecture, which is a very famous conjecture, it's been proven by, recently it's been proven completely for totally real field. Previously, Closel, Harris, Seyfert-Baron, and Taylor, they have proven it for totally real curve with some mild condition on them, and then it got fully proven for in 2011, and even in a generalized version. So if you look at this kind of equidistribution theorem, we will be looking at something similar, but not exactly, but this is the first case which we are considering. I want to talk about another case of equidistribution, which is connected to this one, which is about modular form. So if you think about these modular forms, which are really nice holomorphic function on complex upper half plane, here this H is the complex upper half plane, and you look at all the holomorphic function from this complex upper half plane to C, and they are called modular form if they satisfy some kind of a transformation property. So there is an action of this group gamma naught of n, which is SL to Z intersected with this subgroup. And there is an action of this group on the upper half plane. And with respect to the function has to satisfy a certain kind of transformation. How I really think about this particular property right here, it's about the symmetry. So it tells you something about the symmetry of the function. So if you take n equals to 1, then this function is just, this transformation is simply, it's going to be this translation and this property. So it tells you that if you know the value of the elliptic, of this function inside this region, then you know how the value should be in the other points in the upper half plane and how exactly they are related. So you really see a symmetry. So this is nothing but a symmetry property. So these holomorphic functions are really nice. They have a symmetry. Also, they have to satisfy another condition, which is a growth condition or a bounded net condition. You really should think about that this function has a really nice Fourier series expansion at each cusp. I'm not going to define the cusp, but let's say that this function has a really nice Fourier series expansion. And we'll be looking at mostly the forms are called cusp form. In that case, the coefficient, the first coefficient has to be 0. Okay, so the more boundedness or growth condition. So think about this condition being a growth condition and the symmetry condition, and it's holomorphic. So these are the kind of nice class of function you can think about. And then there is an equidistribution result about the eigenvalues of this or the Fourier coefficients of this. So take all the space of cusp form of level n and weight k. I'm going to denote this space by sk gamma 0 of n. And then the Sato-Tate version of Sato-Tate conjecture for the modular form, it says that these values, so AP of f, these are these Fourier coefficients of the modular form. You can also think of them being some eigenvalues of some operators which I'm hiding behind. And then you take the normalized form of them. They are also equidistributed inside this interval -2 to 2 as your p goes to infinity. P is varying, f is fixed here with respect to some measure. Now this measure is exactly the same one we consider for the elliptic curve, okay? And it turns out that you have the similar kind of, you should expect a similar kind of distribution graph here. And I'm here taking the weight to be any k, but it turns out when the weight equals to k, there is this famous modularity theorem, which says that for every such cusp form of weight 2 and level n, there is an elliptic curve associated to that. So these values I'm considering, they are actually connected. So these two conjectures are connected actually, the elliptic curve version and this modular form version. I'm not really going to consider this version of equidistribution throughout my talk where the p is varying. I'm more interested in the case where the p is fixed and the weight is varying. So there is a version of the equidistribution due to Sayre and other mathematicians where you fix a prime. So you fix a particular prime and then you look at all these values where you are varying your k and n. So as your k plus n goes to infinity, these values are also equidistributed. So they are distributed inside a certain interval, they are equidistributed with respect to certain measure. And that measure is not same as the measure we are considering before. This measure and this measure are not really same. They are related somehow, but not really same. The version of equidistribution I'm going to consider in the talk is going to be this kind of version of the equidistribution. Okay. So really, I want to explain the overall idea behind it, why this kind of question can be interesting. These equidistribution results, they basically mainly come from this classical kind of result from modular forms and elliptic curve, but there are relationship between this modular form or this function which are called Siegel modular form. I'm going to define it in the next slide. So for this kind of nice holomorphic function, there are equidistribution result about their eigenvalues, okay? But there is a connection between these functions and something called automorphic representations of some group. So these are really representation of some groups. For modular form, we consider GL2, and for Siegel modular form, the group GSP4 of our interest comes in, okay? So throughout the talk, I will be exploring the relationship between this kind of functions and the automorphic representation here. And the main question which I'm interested in is this question right here. Are there some equidistribution result for this kind of automorphic representation? can you say something about equidistribution of this representation somehow? Let me remind you, I already mentioned it, that I'm going to consider when the weight is varying. There is a concept of level and weight for this representation as well. And I'm going to consider the equidistribution result when the k is going to infinity. So this is our basic setup. This is the kind of question I'm going to look at. And so the next two slides are going to be defining the Siegel modular form and defining the automorphic representation for this group. So let's start looking at the definition of Siegel modular form, which is nothing but a higher dimensional version of modular forms. So if you understand modular forms, Siegel modular forms are higher dimensional version of them. So you replace the complex upper half plane by the Siegel upper half plane. Okay, similar kind of definition. And then you have holomorphic function from the Siegel upper half plane to C, and it also satisfies a similar transformation property. It's exactly same, only the difference is that this group right here is not living in GL2 anymore. This is it lives in a subgroup of GL4. So these are really 4x4 matrix. So A, B, C, D are 2x2 matrices now. And now we have to consider some kind of a congruence subgroup. So we consider some congruence subgroup of this group called SP4Q. I haven't defined the group yet, but I'll be defining it in the next slide. But there is a subgroup of GL4, and you basically take some congruent subgroup. That means there is some congruence relationship between the coefficients. I'm not going to define all the congruent subgroup which I'll be using here, but I'm going to give you the names. So this one is Kn is the paramodular group. This is the Siegel congruent subgroup. This is the Klingen, and this is the Ivahori subgroup. This one right here, this one is very special one. So this is the same as this is the version of gamma 0n in SL2Z. So if you think about SL2Z subgroup in gamma 0n, this is the version of it in the GL4K. So this corner are all divisible by n and other are in Z. Okay. So I'm going to consider, in the rest of the talks, I'm going to consider the Siegel modular forms or Siegel cusp form really. Cusp forms are, again, there is some growth condition or boundedness condition on them. And I'm going to consider these spaces with respect to these four subgroup and also SP4Z, okay? But I'm not going to define the exact structure of these subgroups. Now that we have talked about this Siegel modular form, we really have to define what does it mean by automorphic representation. So let's start with defining our group GSP4. So this is all the elements in GL4. So this is really a subgroup of GL4, so that it satisfied this symplectic property. So here J is this matrix right here, and lambda is called the multiplier map or multiplier homomorphism. So this is lambda is a map from GL4 to GL1. So it has to satisfy this kind of a property. This group is called general symplectic group. And now if your lambda is always identity map, or this is always identity, then all the elements there is called SP4. So it's like, if this is GL2 version, then this is like SL2, really. So we are going to consider this subgroup right here. If you recall that this SP4 is the one which appeared in the definition of Siegel modular form. So this group is the one which appears in the Siegel modular form definition. So the representation on these groups are kind of related to the Siegel modular forms, okay? But what is really automorphic representation? Automorphic representation, roughly speaking, think about them like a global representation, which are pieced together of local representations. So you have the automorphic representation pi that can be written as a tensor product of representation pi p's, where pi p is a representation of this group over qp. So qp is the completion of q with respect to the p-adic norm. So if you really think about q, so then there is a completion with respect to the usual absolute value, which will be R, and with respect to periodic absolute value, there are these QPs, these fields, and you can consider representation of this group GSP4, with respect to each of these fields, and you will get a representation for each of these P's, and those are called local representation. So I'm going to call them as local representation, and then you piece them together, somehow you get a representation of this group called GSP4, which we are going to call as global representation. Okay, I am hiding all the technicality, just think about it as a global representation pieced together with local representations. And if you are seeing this for the first time, the way I try to motivate this is, if you think about the prime factorization of an integer, then you have a number you can written as a prime power. And for finitely many primes, it depends on what you are doing. The other primes, it's just p to the power 0, right? There is nothing. So similar kind of thing is happening here. You are piecing together the local information to get the global representation. So all the things you need to know about this representation right here is I have to give you the information of these local pieces, right? So I'm going to define some kind of automorphic representation by defining these local pieces, okay? So the next slide, which I'm going to do, is I'm going to give you what kind of local representation we are going to consider. So these are the representation, pi p's, and there is a very deep theory of periodic representation, but for GSP4, it's all classified. The representation we are going to consider, they are pieced together into 6 classes. This slide might be overwhelming, but you don't have to know anything about this slide other than these names right here. There are 6 types of representation, and each of these types can have subtypes also, okay? So whenever I'm going to call my representation pi p's, I'm going to say that, oh, these are type 1, or this is type 2a, or type 3a, and so on, okay? But the representations, this representation right here, if you know about the local representations, these are this Borel-induced representation, which is called, and the one which we are going to consider, these are special one where these characters which appears here, these are so-called unramified character. So they are special kind of characters. So these kind of representations are called Iwahori spherical representation, Iwahori spherical representation. But the only thing probably you should know from this slide is that there are such representation called Iwahori spherical, and they are denoted in, they will be called in terms of their name, which is type 1 or type 2a, and so on. The other thing is, other thing you notice that there are some other information I'm giving you about this representation, which you don't need to remember at all. The only thing you should notice that this tempered one are the one which is a special class of this representation. And we will be focusing on this tempered representation later on in the slide. So, and those are not many, right? So there are this type 1, and then 2a, then 3a, then 4a, then 5a, and 6ab. So these are the only types of representation which are tempered, and we are going to just focus on these types, okay? Now these are this local representation at the place P over QP, but there is also the representation at the place infinity, right? So the usual, if you take the usual absolute value and take the completion of Q with respect to that, then you get R. And the representation of GSP4R, there is a different theory of representation of these Archimedean representations, but the way you should think about that, they are really classified by their weight structure. So there is a weight structure of this representation, and you can visualize this representation on this two-dimensional plane. So each of these weight structure has a minimal weight. The representation I'm going to consider is called, it's called a holomorphic discrete series representation. In that case, your minimal weight is just this k comma k. And the weight structure looks like this. So the weights are going to be here, here, somewhere, like there. Okay, so these integer tuples are the weights. Okay, and this minimal weight right here, k comma k, this thing is really connected to the holomorphic Siegel modular form of weight k. So whenever we are looking at the relationship between automorphic representation of GSP4 and Siegel modular form, this weight k comma k, it's related to this weight k of which happens in the Siegel modular form. Okay, so that's the relation. That's where this is important, that what kind of representation pi infinity you are choosing at the infinite place. Now we have talked about all the kind of local representation we want to consider. So we really are ready to classify our set of representation which we will be looking at today for the set of representation for the equidistribution theorem. So we are going to look at this set SKP omega, where this is a set of automorphic representation. It has to be cuspidal, but I'm not going to in the details. It's similar to it's the one which connects to the Siegel cusp form, not Siegel modular form. Okay, so these are this automorphic representation of GSP4, and there is another extra condition, trivial central character, which needs to be happening. And there are these local information which are totally given at all the places other than P and infinity. It has to be an unramified representation. That means these are this type 1 representation, and with these characters unramified. Okay, so that the characters has to be unramified, and then at the place P, the particular place P, it has to be Iwahori spherical representation of type omega. So this type omega right here, so this can be either type 1 or type 2a and so on. All the 6 classes we had, it can be any one of them. Okay, and at the place infinity, it has to be this holomorphic discrete series representation of k comma k. So this is exactly this representation which shows up here. Okay, so I take this particular class of automorphic representation, and the question I'm studying is this: what are the local local representation pi p's inside this set of automorphic representations are equidistributed with respect to some measure. Okay, now this is the kind of equidistribution result you should expect for automorphic representation. The local representation inside this class of automorphic representation has to be equidistributed with respect to a certain measure. Now the question is, what is this measure, right? What is this measure actually is? So this measure right here, this is this local punctual measure. So if you consider the GSP4QP, there is this measure called punctual measure, which is identified by this property right here, where these F's are all this smooth function on the group, and G hat is the dual group. So that means you're taking the representation on that, and it has satisfied this special kind of property. This punctual measure is, if you think about finite group, then they are related to the dimension squared of the finite group. So it's a widely used measure for studying groups actually. So punctual measure in general, they are supported on the tempered dual. That means that we only can use the tempered representation. So remember that I mentioned in the on the table that there will be tempered representation, the only ones which we'll be considering later on. So we consider this tempered representation. And then we can compute the punctual measure of this tempered representation of type omega explicitly. And the numbers which we get is these numbers right here. So these are the only representation, only types which are tempered. And for each of this tempered representation, we can compute what this punctual measure should be. Now, once you get this punctual measure, then you can really talk about what is the kind of equidistribution result you are looking at. So again, this is the punctual measure. So then with respect to this punctual measure, we get this kind of a theorem. This is the kind of equidistribution result we are getting, is that as limit k goes to infinity, so my weight is going to infinity now, the number of cuspidal automorphic representation inside this set divided by a constant, that has to be same as the punctual measure of this local representation of type omega. And this theorem is true for any one of these representation type I mentioned right here. So how you should really think about this theorem is that the local representation in the set of automorphic representation are equidistributed with respect to their punctual measure. So this set of automorphic representations are really global, but inside them there is this local representation, and these local representations has to be really equidistributed with respect to their punctual measure. That's what the general idea of this theorem is. So the rest of the talk is about counting this SKP omega, which is the number of elements in this capital SKP omega. And this number is actually finite. So the way we get this theorem is explicitly giving a count or counting this automorphic representation. How many numbers of them are there? So what is the method of counting this representation or counting this kind of cuspidal automorphic representation? That comes from explicitly studying this connection, like how this Siegel modular forms are connected to automorphic representation. So you have to go to this nitty-gritty details about it, how they are related. And the fact we use here is that the global representation, global dimension of this space of Siegel modular form, if you think about their dimensions, these dimensions are actually related to the dimensions of space of fixed vector of this local representation under certain compact subgroup. Okay, so if you are exploring this connection between them, then you will see that these congruent subgroups and this compact subgroup, there are this compact subgroup of this pi p, they are somehow related. So I'm going to give you this table that these are the version of congruent subgroup. These are the subgroups of sp4q, and there are the local version of them exactly matching. So this is the subgroup of sp4 of q, and this is the subgroup of gsp4 of qp. Okay, so there is a relation between them, and exploring this relation of this connection between this automorphic representation and Siegel modular form, you get to such a formula. So this is the key formula which we had to explore, that the global dimension of this cuspidal automorphic, global dimension of this Siegel cusp forms are actually going to be the sum over all the representation type times the numbers we want to get times this dimension of this fixed vector. Okay, so you get to this kind of a formula by exploring this connection right here. So now if we want to compute these numbers, these red ones are the ones we want to compute. If we want to compute this number, then if we know this left hand side, and if we know these dimension formulas right here, the local dimension formula and the global dimension formula, then we can it's just about doing some linear algebra to compute it, right? So that's exactly what happens. We are trying to compute this number right here, SKP omega, and omega are this, out of this 6 types, we had to choose the ones which are relevant. So you get on the right hand side, these are the numbers which we want to compute. So this is something we want to compute, and the left hand side, these are these global dimension formulas, and right here, so these guys are coming from these local dimensions. Okay, so if you look at these particular representations and you look at these dimensions, then you get this. Okay, Now you stare at this equation. So this is a linear algebra question of solving these parameters right here. But there are more unknowns than more knowns, right? So it happens that these global dimensions are known by, it's a work of various mathematicians. Here I have named few: Hashimoto, Ibukiyama, Igusha, and Wakatsuki. And these global dimensions, it requires a lot of work to compute global dimension for spaces like Siegel modular form. It's not easy, but so these dimensions are available. We want to use this to compute this side. But since there are more unknowns, we need to get some method to solve this problem right here, right? So this is the reason why I have separated all these classes of numbers we have to compute into further classes. See, there are color, this is really a colorful slide, right? I have this blue color, I have this purple color, and I have this orange color. So blues represent something, purple represents something, and the orange represents something. So what we do is, we look at this representation inside this, we look at them into further classes known as Arthur packets. You don't need to know anything about them. Only thing you need to know that there are this, we are going to consider these 5 types of packets here. And the blue representations are the one for which there would be something in the general type. So this is a G type or general type, there would be a representation here. If this is purple, then that means there is a representation in this P type. This orange one is the one very, very, very special one. You see that this has contribution in general type, in Y type, and also in P types. It sits inside all of these classes, okay? So this has to be treated in a special way. So you look at these further classes of this set, and you divide the set, you write this number as a sum of these 5 numbers, okay? And then you have to compute each of them to get this one, okay? It turns out that these Q and B types, for this, the numbers are exactly 0. So these numbers are always 0 for all Ks and all omegas. So it never appears. In fact, these are the ones which are contributed in weight 2 and weight 1 and weight 2 modular form. So we are not going to consider them. It does not come in the picture. So in the end, we get an equation like this, that we have to compute these SKP omegas. These are this general type, Y type, and this P type. Okay, so these are the numbers we have to compute. Now it turns out, so let's go back to our counting formula. We had this formula. So now these ones, the ones which are in purple color, I'm going to highlight them. So these are the special one, and it seems like we can compute them because they come from GL2 representation or modular form, the elliptic modular form. So you can compute this. So your 2B representation, they come from this space. So this is the over the SL to Z, the cusp form over the SL to Z, and other ones comes from, so this other purple color ones comes from this gamma 0P elliptic modular form space. So remember, I already mentioned that this orange guy right here, so this one right here, this is a special one. And this actually appears in 3 classes. So it appears in P type. So I had to write a P right here. And it also appears in the Oshida type. So I had to write a Y right there. And these numbers can be computed by looking at 2 elliptic modular form. And it's a lift from 2 elliptic modular form. The formula is not, the formula for this one is exactly not this. And I have written star right here. So it's a little bit complicated. But I wanted to mean that they come from elliptic modular form. So there is a way to compute them, okay? So you compute all of them and you compute this one as well. So these are the one which just you can ignore right now. And even if you ignore this, still you see there are, how many of them are there? Still there are 6 of them, right? But there are only 5 in this side, right? So what happens, there is another result or another phenomena we are using, that this 3A and this 6A and 6B, these three representation, they actually come in a pack. So you cannot distinguish the numbers for this one. So we really have to consider them together, and we write this as 3A plus 6AB for the general type, and we consider them as one pack, and we count how many representation are there for these types. Okay, this is coming from a fact from this local representation that the dimensions cannot be looked at separately. So now we really have 5 of them, and we have 5 known and 5 unknown, so we can compute them. Okay, so this is how we compute each of them. So here is a sample result of what kind of result would you expect. This is for 5B, so this is a P type. We explicitly get their this formal series, and we can also figure out what is the number. So it's all totally computable. We have a Mathematica program where we can plug in this P, value of P and value of K, and you compute these numbers right here. This is a very simple one, but the one for this blue colored one, the one for the general types, are very complicated, so which cannot fit into one slide even. The actual formula, it's not that nice looking, but you can actually compute these numbers, and you can see the growth of them, which I have in the next slide. So this is a slide about seeing how the growth happens of these numbers. So here I have picked this particular prime P equals to 11, and I'm looking at this growth. These are the types which are these P types or Y types. So they come from this elliptic modular forms. You see that the growth looks like they are linear. So these are, looks like there is a linear growth right here, right? If you look at all of them, and it turns out that that's how the formula looks like. And if you consider the one which are this G type, or the most complicated type, in that case, you see that you're not getting a really linear, but you are kind of getting some kind of a growth, polynomial kind of a growth. So the type 1 right here, it might look like it's a linear, but it's actually not. It's because this 4A is like, it's growing so fast that it looks like this is linear. But it turns out that all of them right here, they are cubic type. One thing to mention that for each of these ones, so you can see that there are 2 points. There are also 2 lines. There are 2 lines here. There are also 2 lines happening here. This is because of the fact that the weight K can be either odd or even. So you have to look at K odd and K even. For both of them, you get 2 different subsequence of these numbers, and you get this kind of growth. So the main results for these counts are this. For the types which are P and Y type is just O of K. They are linear, and there is a constant which depends on the prime P. And for the other types, the formula for this, these are, I said that this is cubic. So it's explicitly the formula looks like this, where this is the constant which are given for each of them. Now, and the rest of the terms are O of K squared, which we are not considering here. We are not giving the full formula, but there is the full formula is given. You can write down the full formula. But if you notice this number, A omegas happening right here in this global formula right here, they should remind you of our punctual measure for the local representations. And it turns out that they are actually same. So this number right here are actually same as this number. So you get this identity that A omega is same as M omega, but it's a really phenomenon identity you are seeing right here. One side, this is a very local quantity. These are local punctual measure. The other side, these A omegas, they are quantities which are appearing in the global formula of this count. So you are kind of seeing kind of a local global principle here, a connection here. And so that brings us back to the kind of a proof of, so this is a crash course proof of this result here of how you get such a theorem. So if you, so I can give you an example of this the equidistribution formula for p equals to 5, and you can really see that the limits of this side. So I have looked at this ratio right here, and I plugged in this ratio for p equals to 5, and it seems like they are approaching to the measure which we expect. So in this picture, it's probably not very visible. So this is the type 1, this is type 2a, and here this graph is for 3a plus 6ab, and this is 5a, and this is the 4a. And for type 1, the punctual measure is just 1. So you can see the limit here, this is 1. So this is approaching towards 1. For type 2a is p squared minus 1, which is 24 in this case. So this limit is 24. And so on, you can see that all of them are approaching to us, right, the correct thing. So this is kind of a graphical representation of this theorem, which you are seeing right here. So that actually brings me to the final remark. So this theorem right here, even if I just, I'm saying that this is the equidistribution for automorphic representation, this actually sits inside a much more general framework. It can be generalized in many cases. It's actually a case of automorphic punctual density theorem, which was proven by Seen in 2012. There is also many other results. One of the other results I want to mention is by Kim, Wakatsuki, and Yamauchi. They proved the equidistribution of certain holomorphic Siegel modular form, which are not the same ones which we are doing here. There are some different one. But so this kind of result are have a general framework for automorphic representation as well. So these are not very new. These are have been studied for a long time. And in fact, it seems like it is true that you can generalize this formula for prime being, you can vary the prime in a set. You can fix a set of primes and you can vary the prime there. And also you can vary the weight, not being only scalar weight, but you can talk about vector weight, vector valued Siegel modular form as well. And you can get a similar kind of formulas. But these formulas sits inside the general framework of our automorphic punctual density theorem. Okay. There are some other kind of generalization can happen, and I'm happy to talk about it if you are interested. But I would like to end the talk here, and thank you for listening.
Okay, thank you very much. Are there any questions?
I have a question.
Mm-hmm.
So, can you remind me that find the so in your formula, the denominator, there are some powers of prime numbers, 2, 3, 5. Could you remind me, how they come from?
Yeah, so this actually come from a kind of measure you are taking on this automorphic representation, and this constant right here, this is coming from a dimension of complex representation. So this constant right here and this constant right here, they have some meaning. In fact, this constant right here, if you are familiar with the global dimension formulas, then there is this thing called Heisenberg-Mumford volume, and this constant, it seems like they are connected to that one as well. But for our work, when you are looking at this in terms of the automorphic representation, they actually come from a measure of that automorphic representations there.
Oh, thank you.
Mm-hmm.
Any other questions for our speaker?
So can you relate this generalization with your of Kim, Wakatsuki, and Yamauchi with your work? It seems that you can take K and K for K and J. Is that how you get it?
No, it's a little bit different. What they are doing is a little bit different than us. What they are actually doing different is that they are not taking this, they are not considering this Iwahood spherical representation at the prime P. They are all of these representation pi p's, they are all unramified. So this is the reason, this is for all P. So that is the work of Kim, Wakatsuki, and Yamauchi.
Okay.
In that sense, since they are all unramified, they could relate it to something like a vertical Sato-Tate version in some way, because in vertical Sato-Tate version, you take the representation all to be unramified. But in our case, we are taking this Iwahood spherical, so it's a little bit different from what they are doing actually.
I see. Okay. Thank you.
Anybody else? Well, let me venture a question.
Yeah.
It seems to me that these global results that you quoted of those mathematicians for the dimensions of the Siegel cusp forms, my memory is that they depended very heavily on the trace formula.
Yeah.
And I'm wondering whether you could bypass all of their results, go directly into the trace formula and derive your result.
Absolutely, you can do that.
You can?
You can do that, and but you cannot get this nice formula, or so the point of doing this explicitly is that you know how this numbers looks like, you know how this number looks like, so you can just compute this ratio and see that you are getting this limit. But if you are trying to use the trace formula, then it's hard to, so that's what SIN does in automorphic punctual density. They go into the trace formula, and since result is much more general than what we are doing, but since it does a little bit differently than what we are doing. So our case is not really the one special case, but you have to do a little bit differently in the Archimedean place. But SIN is working with these trace formulas, and with the trace formulas, you can prove this kind of equidistribution, but you will not get these explicit numbers right here. You will get it in terms of this some punctual measure and some other quantities right here, like counting this cuspidal automorphic numbers, but you cannot compute them explicitly. You will not get the formula for these guys for if you are going in that direction. Yeah. So getting the formulas for this number, for that you need some knowledge about this local representation and the global representation. I don't know the method of trace formula if they can compute these numbers explicitly. So far what I have seen, nobody is doing them explicitly. They have been just calling them some number, right? So you will have, so I can state this result for a general setting, and I say that, oh, this is the number of counting set of automorphic representation in this class, but I don't give you the number. But the point of this theorem is here that we are giving you what are these numbers in terms of the really numbers, and we are computing this punctual measure as well. But in general setting, you know that this is the punctual measure, you know that this is the counting this representation, but you cannot compute them explicitly.
Well, very interesting, but I bet you that some real good technician with the trace formula might be able to do it.
Probably, yeah.
I don't know, I'm just conjecturing here. One other thing, you mentioned tempered representations. My memory also is that for SP4, the non-tempered representations give you, as it were, counterexamples to the Ramanujan bounds. That's
correct, yep.
Right, so your representations are all going to satisfy the Ramanujan eigenvalue bounds, I guess, huh?
I think so, yeah.
Mm-hmm.
Yeah.
What about doing other groups of rank 2, like SL3 or G2?
I think like I'm mentioning that this, if you follow SIN, what he does, He does it in a general setup for a vast number of group. So GSP4 is one of them. Probably you can consider other group he's considering, but the way his theorem is written in terms of this trace formula, if you want to do something explicit, then you have to translate that in terms of what kind of result you were actually interested in. But since automorphic punctual density theorem is already very general, okay, so you will not the theorem stated in this form, but there will be certain quantities here, there will be certain quantities here, and this side will be some punctual measure. But if you want to do something explicit, I don't know what methods other than this would be useful there. So that's a good question. So right now we don't even know. We are trying to do it for the other representation for GSP4 itself. And since this method of using this global and local dimension formulas are very limited, because you need to know these dimension formulas. So sometimes, so this is kind of getting out of reach. So yeah, so probably there should be some other method using trace formula explicitly. So yeah, I don't know about this. This would be really interesting to think about how you can do this explicit calculation using trace formulas. I'm not good at trace formulas.
Me neither. Well, if there are any other questions for our speaker, if not, let's thank her.
Thank you. Nice work and nice talk.
Thank you.
Yes.
Thank you.
Thank you. Okay, bye-bye.
Bye.